Leetcode 221, Maximal Square. You get a binary grid of zeros and ones. Find the largest axis-aligned square made entirely of ones and return its area, that is side times side. If there are no ones, return 0. Example matrix on screen, a 2 by 2 square of ones in the middle right has side 2, so the answer is area 4. Second example, ones sit on opposite corners, so there is no 2 by 2 block of ones. The largest valid square has side 1, so the answer is area 1. Brute force scans from every one, try to grow a square by checking right, down, and diagonal. That revisits the same cells again and again, so it is slow. Think of each cell as the bottom right corner of some square. The question is, what is the largest square that can end exactly here? Look at top, left, and top left in the DP table. If two sides are big but the diagonal corner is small, you still get a hole. The new cell is limited by the minimum of those three neighbors. Add 1 after the minimum, that counts this cell extending the square built by the neighbors. If any neighbor is 0 on the map, the min is 0, so you only get a 1 by 1 here. Initialize the DP table with zeros. When the matrix has a 0, leave that DP entry at 0. When the matrix has a 1, fill the DP value using the neighbor rule. Each positive entry is the side length of the largest square of ones ending at that corner. Keep the largest side length you see while filling. The problem wants area, so at the end multiply side by side. Build a DP table with 1 extra row and 1 extra column on top and left, all zeros. This zero border removes the special cases for the first real row and column, so DP at I, J only needs the recurrence. Take DP at 1, 1. The matrix cell above left is matrix at 0, 0, which is a 1. Look at its 3 DP neighbors, up, left, and the diagonal. They are all zeros from the border. The minimum is 0, plus 1 gives a side of 1. Now fill the rest row by row. Wherever the matrix has a 1, write the minimum of the 3 DP neighbors plus 1. Where the matrix has a 0, write 0. The largest value reached gives the side of the answer. Look at the recurrence again. Row I only reads cells in row I-1 and row I. Once a row is finished, earlier rows are never touched. So at any moment, 2 rows of DP are enough. Replace the 2D table with 2 arrays of length n plus 1, previous and cur. Walk the matrix row by row. For each j, look up previous at j-1, previous at j, and cur at j-1, take the minimum, plus 1. After each row, copy cur into previous and reset cur. Let m be the number of rows and n the number of columns in the binary matrix. Time is O of m times n, we fill each DP cell once with constant work. Space is O of n when we keep only 2 one-dimensional rows of length n plus 1 for the 0 pad. If you store the entire 2-dimensional DP table, space is O of m times n. Pseudocode for maximal square using O of n extra space, keep 2 arrays, previous row and current row, each of length n plus 1 for the padded column. Walk the matrix row by row and roll previous after each row. M rows and n columns. Guard clause for an empty grid. Best side length so far. Previous DP row, starts as all zeros. Current row we are filling. Walk each row of the input with 0 based index I. Clear the current row before writing new values. Columns 1 through n correspond to matrix columns 0 through n-1. If the matrix cell is a 1, we use the recurrence. Set cur at j to 1 plus the minimum of 3 neighbors, previous j-1, previous j, and cur j-1. Update max side if this cell beats the best so far. A 0 in the matrix forces the DP entry to 0. After finishing the row, copy cur into previous so the next row can read it. The last line returns max side times max side, which is the area.